Okay, so what we had seen is that circular motion is defined as the motion in a two-dimensional plane for a body or a particle such that the distance from a particular point remains constant, and then that particular point is given the name of the center of the circle. So we saw that if we define our origin as the center of the circle and xy plane as, okay, we'll discuss that also soon. Okay, so if we define the origin of our system as the center of the circle, okay, then the instantaneous position of the particle doing the circular motion or in this circular motion at any point of time, the instantaneous position is such that mod r, that is the radius of the circle, should be constant. So O becomes the center of the circular motion. R becomes the radius. Theta is the angular position. Delta theta becomes the angular displacement in any time interval. D theta by dt or omega becomes the angular speed or velocity. And this becomes the angular acceleration. So these are the angular variables. That is one important aspect that we had seen. Okay, and then the other thing we had seen is the two unit vectors, r cap and theta cap. So that is cos theta I cap plus sin theta j cap, and the tangential unit vector minus sin theta I cap plus cos theta j cap. And to that end, we had seen that the position vector at any instant becomes this. So it is in the radial unit vector's direction. And the velocity vector at any instant is this. It is along the tangential unit vector. You can see that velocity has a magnitude of r omega, and velocity is tangential in direction. So velocity is always perpendicular to the instantaneous position. So just review this for a moment, then we'll go back to the application of this in questions, including a question from last time.
Can you explain how you got the tangential unit vector minus sin theta?
Sorry, minus sin theta I cap plus that one?
Yeah.
Okay, so see what is happening here, the tangential unit vector. So if you just draw those two vectors and understand their angles with respect to x-axis and y-axis. So at any instant when the position of the particle is at theta, so the vector r cap is along the line OP, na? In the
Yes.
above diagram.
Yes.
So r cap is like this. So r cap is a vector of magnitude 1 at an angle theta. So its components are 1 cos theta and 1 sin theta. So we have cos theta I cap plus sin theta j cap.
Yes.
So at that instant, where is the theta cap lying? It is perpendicular to this. It's along the tangent to the circle.
Oh, okay, understood. Yes.
So what angle it is making with the x-axis? It is making 90 plus theta.
Okay. Yeah.
So theta cap will become cos of 90 plus theta, which is minus sin theta. and sine of 90 plus theta, which is plus cos theta.
Yes. I only had doubt is that minus sign.
Okay, now it's clear now.
Yes.
Okay, so I'll take you back to the question we were doing in the last lecture and discuss the answers of that one quickly. Excuse me. Okay, so this was the question. Says a particle starts from rest at t equal to 0 with a uniform angular acceleration of this much. So what is the angular displacement after so much time? What is the angular velocity after so much time? And what is the radius? I mean, what is the displacement if the radius is 1 meter? We can also find in this speed v at t equal to 2 seconds. That's another thing we can find. You can add that to the. So see the information that is given in the question. It starts from rest at t equal to 0 with uniform angular acceleration. So angular velocity initially is 0 at t equal to 0 and alpha is uniform. So it's constant. So alpha is constant means rate of change of angular velocity is constant. So that means angular velocity at any time should become initial angular velocity plus alpha t. Okay. Just like in 1D motion, if acceleration is constant, then velocity at any time becomes u plus at, and displacement at any time becomes ut plus half at square, and v square becomes u square plus 2as. So like that we can use similar equations here. Angular displacement at any time like this. Okay, so you're just changing the linear variables to angular variables. So we can use these three equations if alpha is constant. Omega naught is the initial angular velocity, that is at time t equal to 0. So in this case, using this, we'll see that angular velocity at any time will become pi by 16t, and angular displacement at any time will become pi by 32 t square, because omega naught is 0 and alpha is pi by 16 radians per second square. So this will be radians. So the first part, at t equal to 2 seconds, you can see that the angular displacement would have become, the substitute t equal to 2, so pi by 32 into 4, so pi by 8 radians. So it's gone 45 degrees along the circle in that much time. And again at t equal to 2 seconds, angular velocity is pi by 16 into 2, so that's also pi by 8, but that's in radians per second. Now the third part is not something we can get directly by the formula, because there's no direct formula for linear displacement, so we have to find displacement in 2 seconds. So we'll have to make use of what we have calculated in the first part, the angular displacement, this much, okay. So from, and the radius is given to us, so from that what can we tell about the displacement? Okay. So actually we can only find out the magnitude of the displacement here. Okay, so just try this part out, people. So the hint I'm giving you for the third part is that you have to actually draw the circle, and
So like we have solved it, but like the answer was little bit different kind of.
answer is how much?
Sir, I got like shall I say from step by step or directly answer?
Okay,
Uh,
you can send me the answer in text message also if you've done it.
okay, sir.
I'll verify if it is correct. You should be able to get the answer numerically in meters, right?
So, but like there were very pretty unusual angles, so it was a bit different.
Okay. No, the answer is not correct. Okay, the hint to you is that just draw the diagram of the circular motion, okay, and understand that pi by 8 is how much actually? 22.5 degrees, no?
Yes, sir.
So yes, you will get a tricky kind of answer. But whatever the answer is, see, it will be less than the radius. It will be less than 1 meter.
Okay, sir.
Okay. So do one thing. Let's do this in two parts. Okay, let's calculate the displacement from 0 to 2 seconds is fine, but that will give us a very, and also
Sir,
0 to 4 seconds. Yes,
sir, what is the difference between angular displacement and the normal vector displacement?
it's not a difference, no, but normal displacement is a linear vector, no? It's in meters and it's a straight line joining the initial to the final position. Angular displacement is a change in angle, no? It's in radians.
Okay, sir, got it.
They are two different physical quantities, no, altogether.
Yes, sir.
Okay, so let's understand this now. Angular displacement formula, which was pi by 16, sorry, pi by 2t square. Radians is that if you visualize the circular motion, let's say the particle started from here at t equal to 0. This was the position. So at t equal to 2 seconds, the angular displacement we have seen is pi by 8. That would be somewhere here. And at t equal to 4 seconds, the angular displacement would be pi by 2 or 90 degrees. So the second one is quite easy. The first one, you'll have to actually use a calculator to find. So this is where it is at t equal to 4 seconds. So the first one's answer is basically this now. So you have to calculate the magnitude of this vector. This is the displacement from 0 to 2 seconds. And the second one's answer, you have to calculate
So we can use that Pythagoras in that.
the second one you can just use isosceles right angle triangle, so Pythagoras. Okay. So now let's concentrate on the first part. So it's a little tricky, but there is a method. Okay. And you can make use of vector algebra also. So this is like your B vector, this is your A vector. They're both of the same magnitude, and the angle between them is theta equal to pi by 8, and their individual magnitudes are 1 and 1 meter. Okay. So the radius of the circle is given to us as 1 meter. So what is the magnitude of this difference of B minus A going to be? You can make use of that. So I have that theorem that if mod B is equal to mod A is equal to A, let's say, then the magnitude of B minus A or A minus B, whichever, is 2A sine theta by 2. Right? Whereas the magnitude of A plus B is 2A cos theta by 2. So you can make use of this formula here. So the displacement is this triangle only I've drawn again here, but taking the vectors as capital A and B. So the displacement from 0 to 2 seconds will have a magnitude of 2 into this thing being radius 1 meter into sine of pi by 16. So that is where you will have to bring in your calculator thing. Okay. So 2 sine pi by 16 is the same thing as 11.25 degrees. It will be a very small displacement in that sense. So it will be about 0.39 meters, close to 0.4. Okay. Where is the, so this is the this part. The B part is very simple. You can see that the displacement from 0 to 4 seconds is have a magnitude of root 2r, 1.4 meters approximately. So one more thing you can observe is during the entire circular motion, the maximum possible displacement from starting is 1 diameter.
Yes, sir.
That happens when the angular displacement is pi. Okay, and the fourth part of the question, we wanted to find out the linear speed at 2 seconds. So that's very simple. We'll use the formula V is equal to R omega. So R is given to us as 1 meter, and omega we have found out at 2 seconds is pi by 8 radians per second. So V equal to R omega will give us the speed.
What was the fourth question again?
Sorry, come again, Meta.
Fourth one.
Come again, what?
Fourth question.
Fourth question, yeah. Fourth question, we have to find the linear velocity, that is V. Yeah, we have to find V at 2 seconds. Okay. So for this, we'll just use the relation that V is equal to R omega. We were talking about this earlier. Okay. So V is equal to R omega means this is 1 meter into, now what was omega at 2 seconds? Omega at 2 seconds we had seen was pi by 8 radians per second. So okay, so now from angular variables,
Sir, sir, I didn't wrote those things. Can you?
okay, let's move on to,
Sir, can you please scroll up?
yes, I'll scroll up just a moment.
Sir, can you go a bit down?
Can you scroll down?
Okay, so let's move on to the next part. Now, after having understood the angular variables, we will get into understanding of the kinematical variables, position vector, so velocity vector, and acceleration vector in a circular motion. So if at a certain instant of time, the angular position of a particular particle in circular motion along this circle of radius r, if the angular position is theta, that means the position vector or the line joining that particle with the origin, that itself is making an angle theta with the x-axis. So position vector is r cos theta I cap plus r sin theta j cap, or write it as cos theta I cap plus sin theta j cap. So that is the same thing as r cap, where r cap is what we call the radial unit vector. So it is a unit vector along r, that is the position or the line OP. So this is a special unit vector for us in circular motion. We just saw this. So we will see that henceforth all vectors like acceleration, velocity, force, etc., they will be expressed in terms of two unit vectors, radial and tangential unit vector. Instead of I cap and j cap, when we are practically applying the concepts, we will resolve things in terms of radial unit vector, which is a unit vector of magnitude 1 along this radial line, and tangential unit vector, which is a vector of magnitude 1 along the tangent to the circle. So, tangent.
Sir, what is written after acceleration A in a
Circular motion. CM we can use as a short form for circular motion.
Sir, so means that among these three parameters like velocity, position, and acceleration, when we will see them in radial and this tangential unit vectors, so they want to comprise like both of them like together, like we have in I cap and j cap, that there might be a vector in between them two. Either it will be only tangential vector
Yes,
here.
in the case of acceleration, that will happen. You
Acha,
would have heard of the term centripetal acceleration, right?
yes, sir, it's towards the center.
So centripetal acceleration will be the component of acceleration which is along minus r cap. But there is also a term called tangential acceleration in circular motion, and that is the component of acceleration which is along theta cap. But when it comes to velocity, we will see that the velocity does not have a r cap component. It only has a theta cap component, which is what tells us that the velocity in a circular motion is always in which direction? The tangential direction.
Yes, sir.
So next thing, but how do we show that? Actually, we show that from the definition of velocity. That instantaneous velocity is rate of change of position or displacement, whichever, with respect to time. So here we will express the velocity vector as rate of change of position vector, which we have seen as this. So in this expression now, r is a constant, I cap and j cap are constants. So the differential operator applies directly on cos theta and then again applies directly on sine theta. And now to execute these differentials, we will make use of chain rule. That is differentiation with respect to time of cos theta will become derivative of cos theta into d theta by dt. And that is minus sine theta into omega. So likewise, we can also work out what will be the time derivative or rate of change of sine theta, like I've done for cos theta here. Like this, you work out what is it for sine theta so that you can express this next step yourself.
Omega cos theta.
Yes, very good. That will be omega cos theta. So put that now, and from that, in the vector equation, if you put it, so you'll be able to show that the velocity has a direction which is tangential. So just try this yourself.
Here by velocity, you mean angular one?
Okay,
Sir,
so yes,
by velocity, you mean linear velocity.
velocity is just the definition of velocity vector. It is rate of change of position or displacement. So it can be called yes, linear velocity or translational velocity. So substituting these here, we can see the instantaneous velocity becomes r into minus omega sine theta I cap plus omega cos theta j cap. So next step, you can take your omega also common. So you're left with this. Now this is nothing but the tangential unit vector. So the velocity is r omega into theta cap So that means velocity does not have a radial component, which totally makes sense because it's a circular motion. So this shows us that the magnitude of velocity or the speed is related to the angular speed by this relation, which we already saw in that question above. Okay. And velocity's direction is tangential in any circular motion. At any point of time, wherever the particle is located, the velocity vector of the particle will be along this sort of direction. Along the tangent. If at a later time the particle is located somewhere here, so its position vector has become r1, then at that instant the velocity vector will be along this such that it is perpendicular. So always this relation will hold true, that the velocity's direction is tangential, hence perpendicular to the position vector.
Sir, these formulas are applicable only in the case when our angular velocity is constant, no? Not like any
No,
constant.
this is instantaneous angular velocity. Omega may be constant, may be variable, but velocity is always related to omega by v equal to r omega. For example, if omega is increasing, then the speed is also increasing. If omega is constant, then the speed is constant.
Okay, sir.
So till now, whatever we have discussed is for general circular motion, whether it is uniform circular motion, that is at constant speed or constant omega, therefore, or it is the non-uniform circular motion. So next we are going to classify uniform and non-uniform circular motion, because we will see that when it comes to acceleration, there's a difference in the acceleration of the two cases, uniform versus non-uniform. But up to velocity, the formulae are the same, whether you are talking about uniform or non-uniform. The difference is in uniform, V is constant in magnitude. In non-uniform, V becomes variable.
Yes. And that's because the change in omega ka value, right?
Yes, because omega is variable in non-uniform, okay, whereas in uniform, omega is constant in magnitude. Okay, so next we will discuss about acceleration, but before that, we will look at the classification of circular motion into uniform and non-uniform circular motions. So a circular motion at uniform speed is classified as uniform circular motion. Henceforth, we will refer to it with the synonym or with the initials UCM, whereas a circular motion at variable speed is classified as non-uniform circular motion. So you can think of circular motion divided into two categories. Uniform circular motion happens at constant speed, but not constant velocity, mind you, okay? Because the direction of velocity is always changing. So we should not say that uniform circular motion is at constant velocity. It is at constant speed or uniform speed. From this, we can also see that in uniform circular motion, since speed is uniform or constant, therefore omega is also uniform, because we have the relation V is equal to R omega. So if V is constant, then omega is also constant, which means alpha is 0, because alpha is d omega by dt. Whereas in non-uniform circular motion, V is variable. So it means that omega is also variable, which means that angular acceleration alpha should be non-zero. Okay, so that becomes additional difference between these two. Constant speed, variable speed. So that also means constant angular speed and zero angular acceleration for UCM, whereas it makes variable angular speed and non-zero angular acceleration, non-zero alpha for the case of non-uniform circular.
So,
Yes.
so we can say that in uniform circular motion, the acceleration, like the linear one, it represents the change in direction of velocity. But
Yes.
in non-uniform, it represents the change in the magnitude of velocity along with the direction. So like it must complement
Yes.
in both the cases.
Yes. That is why we will see that there is one difference in the acceleration in the two cases. In UCM, the acceleration is only centripetal. It's only pointing towards the center. There is no tangential component of acceleration. Whereas in non-uniform circular motion, we will see both the components are there because the acceleration's job is to both change the magnitude of the velocity as well as keep turning its direction. Understood? No?
Yes, sir.
So in fact, that's why it's important to understand the classification into uniform and non-uniform before we come to acceleration in circular motion. Yes. Acha, you are writing down, yes. Okay. So example of a uniform circular motion would be the seconds hand of a clock. Example of a non-uniform circular motion would be a car moving on a circular track with increasing or decreasing speed. And one more important point to understand about uniform and non-uniform circular motion is that uniform circular motion, it is a periodic motion. That means the motion repeats itself in cycles of same time period. So it's a periodic motion with a time period of this or this. Whereas non-uniform circular motion is a non-periodic motion. It does not repeat itself in definite time periods. So it does not have any so-called time period because every cycle happens with a changing time. Okay, let's come to acceleration now. So straight away we will look at acceleration in two categories. Okay, we will look at, first of all, acceleration in uniform circular motion. So in uniform circular motion, the acceleration, which is defined as rate of change of velocity with respect to time, velocity being r omega theta cap. Now here r is the radius, which is constant. Omega is constant in uniform circular motion. So the acceleration directly becomes r omega into rate of change of theta cap. Now theta cap is the tangential unit vector which is changing with respect to time, because it's all the time turning as the particle is turning. So this becomes rate of change of minus sine theta I cap plus cos theta j cap. Now I want all of you to work this out yourself, the steps ahead, and show why it will become this. Okay. So from the second last step to the last step that I'm writing, there is that entire differentiation by chain rule and all involved. So I want you to work that out yourself and show that the acceleration becomes like this.
Yes, sir, like I already did it before this.
This is the chain rule. Minus sine theta becomes
Yes.
minus
very
cos
different.
theta omega,
Omega. Very good. That's
and
correct. Okay.
cos theta becomes minus sine theta omega. Negative is common, and then omega common.
Sir,
Yes.
sir, like if like just extra thing, application based. So our Earth's revolution around the sun is like variable thing, non-uniform acceleration. So if we find this non-uniform acceleration centripetal component, so from that we can find that the force with which the sun is pulling us towards it.
Exactly. And that is the gravitational force.
Acha, sir.
So
Okay, so
any planetary orbital motion, or any satellite in orbital motion around a planet or whatever, it has that principle that the centripetal acceleration is provided by the gravitational pull. Okay. But the only difference is that the Earth's motion around the star, around the sun, is not a circular motion. Actually, it's an elliptical orbit.
yes, sir.
Only artificial satellites, man-made artificial satellites, have perfectly circular motion around planets or particularly around the Earth. And because for that, they need to be projected with a certain calculated velocity so that they achieve the circular orbit. So that doesn't happen in natural astrophysical systems. It only happens in artificial satellite cases. Okay. And yes, in those artificial satellite cases, what will happen is that it will be a uniform circular motion. They have a definite time period.
Yes, sir. So, but like in this elliptical thing also, we might get a close answer to our normal gravitation acceleration, or like it will be a vast difference.
See, even in elliptical orbit, there will be a component of force towards the planet or star, whichever is at the so-called focal point of the ellipse. Okay, and that is because of gravity only. And gravity is the agent which is providing the acceleration.
Okay. Okay. So means that the Newton, when he found that acceleration, so he might have used this method. Like,
Yes, yes. Like the whole derivation of elliptical orbit and all that was on the basis of this thing only.
okay.
There's something called Kepler's laws. We'll study in the chapter of gravitation. So in Kepler's laws, we'll understand how the concept of gravitation and then kinematics of orbital motion are linked to each other. Okay. And yes, Sai, to answer your question, the Earth's motion around the sun is accelerated, because both the direction and magnitude of velocity is changing all the time, because it's an elliptical orbit. Okay, if you talk about a artificial satellite in circular orbit around the Earth, it is a uniform circular motion actually. So there is no tangential acceleration. There is only what we call centripetal acceleration, what we are learning now. Okay. This is our rate of change of theta. So this acceleration is called the centripetal acceleration, because it points to the center of the circular motion, because its direction is minus r cap and its magnitude is r omega square or v square by r or v into omega. So these relations can be interchanged because v is equal to r omega. So replace omega with v replace omega with v by r. You can see you'll get the second relation, not this third relation. So in uniform circular motion, the acceleration vector points to the center at all times. It's called a centripetal acceleration. And has a constant magnitude. It's not a uniform acceleration because the direction of acceleration is changing, but if the magnitude of acceleration is uniform.
Sir,
Hmm.
so in this uniform circular motion, acceleration only changes the direction of the velocity vector. Right?
Yes, it's a centripetal acceleration. Job is only to change the direction of the acceleration because the magnitude of the speed is constant.
Yes.
Okay. Now, next up, let's understand about acceleration in non-uniform circular motion. So this is where we'll see that acceleration has two components, tangential and centripetal. Because when we define acceleration as rate of change of velocity and therefore rate of change of r omega theta cap, now only r is constant. Both theta cap and omega are variables. So here omega is a variable and theta cap is also a variable. Only the radius is constant. So we have to use the product rule. So this will become r comes outside, but into differentiation of the product of these two. So we can write it as differentiation of the first term omega into theta cap plus omega into differentiation of theta cap. We can do is keep the cap, the radius outside altogether. Now you can see that differentiation of omega with respect to time is defined as alpha, the angular acceleration, and differentiation of theta cap with respect to time we just saw in the previous section is minus omega r cap. Okay, just saw about. There's something. Okay. So this becomes r into alpha theta cap minus omega square r cap. So basically it becomes the acceleration vector is r alpha theta cap minus r omega square r cap. So we say it is the sum of two components, tangential and centripetal. Where this is called the tangential component of acceleration. And this is called the centripetal component. So in this case, centripetal is just a component of acceleration. It is not the net acceleration. In the case of uniform circular motion, alpha is 0. So automatically you can see that tangential acceleration becomes 0. So this acceleration's expression reduces to purely centripetal. So you can also think of uniform circular motion as a special case of this, where it is the situation where alpha is 0.
Sir? sir.
Okay, so if you look at this situation visually now, we'll understand that in non-uniform circular motion, there are two components of acceleration to the particle. So for a particle at an instantaneous position like this at some point of time, the acceleration in general can say will become a vector which is in some random direction like this. So the acceleration vector now consists of two components. A centripetal component points like this, and a tangential component points like this. So additionally, we can see that since the net acceleration is the sum of centripetal acceleration plus tangential acceleration, centripetal acceleration being minus r omega square r cap, or minus of v square by r cap. So magnitude of centripetal acceleration is r omega square or v square by r. Okay. And tangential acceleration is r alpha theta cap. So the magnitude of tangential acceleration is r alpha. So this can also be written as, so since r is a constant, so we can see that it is this. So the tangential acceleration can also be expressed as this, which means that tangential acceleration equals to rate of change of the speed of the particle. basically, from this we can understand that tangential acceleration changes speed or magnitude of velocity, okay, whereas centripetal acceleration changes the direction of the velocity continuously. Okay. So it keeps it turning. It keeps the velocity vector turning continuously. Whereas tangential acceleration will be responsible for any change in speed. So therefore, in uniform circular motion, tangential acceleration is zero because there is no change in speed. Okay, so let's look at some example questions.
Sir,
Yes.
there's a question. For the case of inclined curved plane, we will have an extra k component, or it will be same.
No, see, the thing is, whether it's on an inclined surface or it's a vertical circular motion or a circular motion on a horizontal plane, ultimately circular motion is a two-dimensional motion. Just the plane is changing. So everything is related to this one. There are only two possible cases, uniform and non-uniform. Okay.
Sir,
Okay.
Yes.
sir, the AT vector is R alpha into theta cap, but in the next step, where does it go?
Sorry, come again.
Sir, the R alpha theta cap is there.
Yes.
The acceleration through the tangential path. So in the
Yes.
next step, where does the theta cap go?
Sorry, come again.
In the next step,
Uh,
so where does the theta cap go?
theta cap is the tangential unit vector. No? It's the unit vector in this direction along the tangent. Understood? No?
Yes, sir.
Okay. And radial unit vector is this one, r cap. So minus r cap is pointing towards the center. Clear?
Yes, sir.
Okay. Now, one more thing that we should understand from this is that since the net acceleration is the vector sum of tangential acceleration and centripetal acceleration, and these two are perpendicular vectors, as you can see. So there is also this relationship that the magnitude of the acceleration is square root of the tangential acceleration square plus centripetal acceleration square.
Sir, done copying.
Okay, done now.
Yes, sir.
Okay. Now let's look at some numerical examples. A particle is in uniform circular motion of radius 10 meters at a speed of 36 kilometers per hour. Find its angular speed, its angular acceleration, and acceleration. Find the time period of its cyclical motion. Okay, so just try this out, people. Yes, very good, Jinint. That's correct. And the unit will be radians per second, right?
Yes, sir. Sir, in the second one, we will get a function like alpha.
So that you have to figure out. You mean the time period?
No, not the time period. This centripetal angular acceleration.
No, it will be a very simple answer. Just
Okay.
go back to the definition of uniform circular motion, you'll understand.
Sir, is my second one correct? Like the logic one?
Yeah, I'm just going through. Okay, so let's understand. So it's a uniform circular motion. So what we can say about alpha, it has to be 0. That's correct. Okay. And omega and v have what relation? V is equal to r omega. Okay. So because it's a uniform circular motion, so we can say that alpha is 0 and v equal to r omega is a uniform speed. So omega is v by r. So in this case, 10 meters per second divided by 10 meters. To convert, okay. So omega is 1 radian per second. And alpha is 0. And linear acceleration is omega square r or v square by r. That is only centripetal acceleration. That is going to be 10 meters per second square in magnitude. Okay, the direction is always changing. So that's the first part. Okay. For the second part, the time period is 2 pi seconds or so much.
So here we'll call acceleration variable or constant.
Yes, acceleration is variable because the direction
So
is
the
changing.
direction, yeah.
But magnitude of acceleration is uniform. So wherever the particle is located, it has an acceleration of magnitude 10 meters per second square, pointing towards the center. For example, when it is here, when it is here, doing this at a constant omega. Okay, now let's come to the third part. Angular displacement is going to be omega into time because omega is uniform. So angular displacement is going to be 1 into t in radians. So at t equal to pi by 3 seconds, the angular displacement is pi by 3 radians. So the angular displacement is pi by 3 radians. You can see that it has covered 1/6 of a circle. So a full circle is 2 pi. So the linear distance traveled, or rather the linear displacement, will become equal to the radius. And the distance traveled, so if it was here at t equal to 0, then after pi by 3 seconds, be here. Such that this angular displacement will be pi by 3. So you can see that the linear displacement will be this. So this will be an equilateral triangle. So at this time, but the distance traveled,
It will be the arc length of that.
it will be the arc length. So like this. Sorry, the radius is 10 meters. The magnitude of displacement, correct, is 10 meters. So you can see that this is slightly greater than 10 meters. This is going to be approximately 4 7.
Sir, how
You can
did
see
you
this
get magnitude of distance as 10 meter?
magnitude of displacement better, because see the diagram over there on the left, it's a equilateral triangle. No? Because this angle is 60, the other two angles are equal because radius and radius are equal. So becomes an equilateral triangle.
Yes, sir, got it.
Sir,
Yes.
sir, the
Yes.
motion of the particle is uniform. So if the motion is
The
uniform, then
what is uniform, beta?
the motion of the particle.
No, it's not a uniform motion. It's a uniform circular motion. Uniform motion is motion along a straight line with uniform velocity. Understand? They are different things.
Yes, sir. So acceleration should be zero now, since the
That is the whole point, na, beta. It's not uniform motion. It is circular motion. The velocity's direction is changing, na? So how acceleration will be zero?
okay, sir, got it.
Understood? Na? Tangential acceleration is zero because speed is constant. So uniform circular motion. So tangential acceleration is zero. But centripetal acceleration still has to be there, na? Because it's a circular motion.
Yes, sir, got it.
I noted.
Okay, so with this we complete today's session. Next time we will look at more examples. So with this actually we finish what is called kinematics of circular motion. So next lecture we will look at dynamics, that is how to apply Newton's second law and discuss about the net force or forces acting in circular motion. So that is where the concept of acceleration becomes important, because net force is equal to mass into acceleration. So we will utilize all these equations that we have derived today in the next lecture also. So that's it for today's session, people. Wish you all the best. Have a nice day.
Sir,
Thank you, sir. Bye, sir.
Bye, sir.
Thank you, sir.
Thank you,
sir.
sir. Thank you, sir.